Now, it was mentioned in the reading that the standard normal distribution is a mound-shaped distribution with average 0 and standard deviation 1. And all of the values in this distribution are their own z-scores. So in some sense, the standard normal distribution is a set of z-scores for mound-shaped distributions. Because of this, they use the letter z for the random variable for the standard normal. Now the table gives cumulative probabilities for areas under the curve of the probability density function that models this distribution. So now, how do you get these cumulative probabilities using the table? Ultimately, we're going to use these to solve all of the probability questions for mound-shaped distributions. But how do you work the table to get these probabilities? Well, let's start out here with a series of questions. What would be the probability that in a normally distributed data set that I would pick out a value and its z-score would be less than, say, negative 1.52? To use the table to find that value, I see that the rows are the z-values and the columns are the z-values. So to get the negative 1.52, I'm going down to row negative 1.5 and over to column 0.02. So in row negative 1.5 and column 0.02, I get 0.0643, or approximately 6.4%. So in a mound-shaped distribution, if I reach in and pull out a data value, what's the probability that that data value z-score is going to be less than negative 1.52? That's 6.4%. Or 6.4% of the values in a normally distributed data set have z-values less than negative 1.52. Okay? B. What's the probability that z would be less than 2.2? So if I had a normally distributed data set and I reach in and pull out a value from that data set, what's the probability that its z-score would be less than 2.2? Now for 2.2, I've got to go to page 2 of the table where the z-scores are positive. And I'm going to look down to row 2.2 to start. Now since that's the entire number, I'm going to stop in column 1 that's labeled 0.00. So I see the probability there is 0.9861, which is approximately 98.6%. So 98.6% of the values in a normally distributed data set will have z-scores less than 2.2. Okay? Or if I reach into a normally distributed data set and pick out a value, what's the probability that that value's z-score is less than 2.2? It's 98.6%. Okay? Now, let me draw little pictures here. The first one that I looked up, the z-score was negative 1.5, negative 1.52, and I looked in the table, and the table gives me the area. Table always is going to give you the area under the density function or the probability of being less than whatever the value is. So I get 0.0643. In the second case, again, standard normal distribution, and this time I'm at 2.2, and the probability question is what's the probability that the random variable will be less than the 2.2. Again, that's the area to the left of the value, the z value, and under the density function it's going to give me the probability. The table does that. 0.9861 is the number I get in the table. Now let's look at one that's a little bit different. Let's find the probability that z is greater than a negative 1.75. A negative 1.75. In that case, remember it's the area under the density function above the interval. So I'm going to be down here at a negative 1.75, but I want the probability that the random variable is going to be greater than that. So that interval is going to be to the right of negative 1.75. So the area is under the density function to the right. Now, when I use the table reads to the left. It's always to the left. So when I look up a negative 1.75, and that would be, again, in the first page of the table where the z values are negative, I'm going down to negative 1.7 and across to column 0.05, and I get an area, again to the left, 0.0401. So the probability that z would be less than negative 1.75 is 0.0401, but I don't want that. I've got the probability of z being greater than negative 1.75. Remember, back from the uniform distribution, what we learned about probability density functions is the probability always adds up to 100%, so the area under the curve adds up to 1. So to get the shaded area above the negative 1.75, I have to subtract the 0.0401 from 1 to get my answer on this one. So I get 0.9599, which is approximately 96%. So in a normally distributed data set, if I reach in and pick out a value, the probability that the z-score would be greater than negative 1.75 is 96%. So again, I'm looking at the normal probability density function modeling a standard normal distribution where the average is 0 and the standard deviation was 1. But the cleverness about this is that this distribution is a set of z-scores. And ultimately, from the z-score formula, I will be able to relate all of the normal distributed data sets to equivalent z-scores and use this same table to do all of the problems. So we were going to be using this standard normal table a lot. Now, just to make another connection here, let's try another problem. What's the probability that the random variable will be between negative 1 and 1? In other words, if I go into a normally distributed data set and I reach in and pull out a value, what's the probability that the z-score of that value will be somewhere between negative 1 and 1? In other words, what's the probability that the value itself will be within one standard deviation of the mean? Okay? Now, if you remember, the empirical rule said that's approximately 68%. So let's use the standard normal table to find out more precisely what it is. Now, first thing I'm going to do is I'm going to sort of shade the area under the density function above the interval. And remember, this standard normal table is a set of z-scores. So I'm going from negative 1 to 1. I'm talking about this interval right here. The probability of being in an interval is the area under the density function above the interval. So this is the area I want. This is the answer to the question. The area is the probability. Now, to do that, I'm going to have to look up two numbers in the table. First, I'm going to look up -1. Now, -1 is down in the first page of the table, down to -1 row, and that's all it is. So the column is 0.00. I get 0.1587. So remember, the table always reads to the left. So the area to the left of -1 is the cumulative probability is 0.1587. If I look up 1, I'm going to page 2 because that's a positive z-value, and I go down to row 1. And that's the entire number, so I'm going to stop at column 0.00, and I'm going to get 0.8413. Now I'm going to put that in red. So again, the table always gives you cumulative probabilities to the left. So the area to the left of 1, which I've shaded in red, is 0.8413. Okay, so what is the probability that is of my black shaded region? What's the probability of the black shaded region? Well, I would take the red, subtract the green. The red is the accumulated area up to 1. The green is the accumulated area up to -1. If I subtract those, I'll get what I want. So I'm going to take 0.8413, and I'm going to subtract the 0.1587 to get 0.6826, which is approximately 68%. So what we've calculated here is that approximately 68% of the values in a normally distributed data set will be within one standard deviation of the mean. So this is what the empirical rule said. The standard normal distribution is the set of z-scores. So it's really an extension, a refinement of the empirical rule. Now, what the empirical rule didn't tell us is what if we want the probability that z would be somewhere within 1.5 standard deviations of the mean. 1.5 standard deviations. We didn't have that one with the empirical rule, but now we do. We've basically, through the standard normal distribution, refined the empirical rule. And now we have more than the empirical percentages. We have the probability of being in any subinterval, not just within 1, 2, and 3, but any subinterval. For example, what's the probability in a mound-shaped distribution that a data value will be within 1.5 standard deviations of the mean? Well, to calculate that, I would do it in pretty much the same way. I would have to look up the accumulated area up to 1.5, and in the table that would be 0.9332, and subtract the accumulated area up to -1.5, which would be 0.0668, and I would get the probability 0.9332 subtract 0.0668, I would get 0.8664, or approximately 86.7% of the data values in a normally distributed data set will be within 1.5 standard deviations of the mean. So I'm now back to the empirical rule, but I'm extending it now. I'm able to find the probability of being in any subinterval, as illustrated by these examples. This is the set of z-scores, and this is what we will be able to use to find the probabilities of being in any interval in any normally distributed data set. Let's do one more here. What's the probability that the random variable, or the z-value, will be somewhere between a -0.32 and a 1.5 1.49. Again, it's going to be pretty much the same as the last two. I'll have to look up the 1.49 first, and that would be over there on the positive Z, page 2 of 1.4, but across to row 0.09. So that would be 0.9319. And then the negative 0.32, I go down to row negative 0.3 and over to column 0.02. So that give me 0.3745. And I could subtract those to get 0.5574, which is approximately 55.7%. So, in these several examples, it's starting to get comfortable in how the table works. You look up a z-value, and you find the cumulative probability up to that z-value. It's important to note that the table always reads to the left. So, you're getting a cumulative area under the density function or the probability to the left of your z-value. Now for A and B, the table values were exactly what I wanted there because I was asking the probability that Z was less than. But in C, I was asking the probability that the random variable was greater than. And again, the table still reads to the left. So to get the area that I wanted, I had to subtract from 1 the value I got from the table. It's very important to remember that this is always going to work this way. And I think the best way to approach these problems is to draw a little sketch and try to figure out, first of all, what interval you want to find the probability for, and then find the area under the probability density function above that interval. Shade that in, and that area is your probability. In the case of problems D, E, and F, very important again, always realizing that the table reads areas to the left. And how am I going to use those to get those problems? I have to subtract to do that. So I think in all these problems are represented the 3 different types of situations you're going to be in. You're going to be to the left of a value, which will work very well with the table. You're going to be to the right of a value, which you'll have to subtract from 1 to get that. Or you're going to be somewhere with an upper and lower value, like D, E, and F. And in that case, you're going to look up 2 values from the table and subtract them. I also want to point out something important to realize. Since the standard normal table is a set of z-scores, you'll notice that the table does not go much to the left of -3 or much to the right of 3. Remember, the empirical rule says almost all the data values are within 3 standard deviations of the mean. So anything that has a z-score less than -3 or a z-score greater than +3 is an outlier. So there's not much probability there. Let's look at one more example to illustrate that. What if I had the probability of Z being greater than 4? So Z being greater than 4. And let's try to draw a picture of that. Now I have my standard normal distribution, but then I have 4, which is really an outlier. It's beyond the table. It's further out than most any of the values. It would be any value with a z-score of 4 would be an outlier. And what's the probability of being in the interval greater than 4 or to the right of that? So I'm talking about this interval starting at 4 and going to the right. Now, if you're thinking about the normal curve is really, this curve kind of falls closer and closer to the horizontal. It's sort of an asymptote line there. The curve never ends, it just keeps going, but it flattens and gets really close to the horizontal line that it's above. But if I look up 4 in the table, there is no 4 in the table. But it does go out to 3.09, and the probability there is 0.999. So I would approximate the probability to the left of 4 at being really 1. So let me go ahead and shade that area to the left of 4, because that's the table's giving me those values. Always to the left with the table. So okay, well, according to the table, that whole cumulative area is 1. So to the left of 4. But I want the probability of being to the right. So what do I have to do? As in problem C, I would have to subtract from 1. So I'm going to take 1, subtract 1, and get 0. So what's the probability of being further out than 4? It's practically 0. Now, in the true mathematical sense, again, that normal curve, the horizontal is an asymptote line for it. So it never really gets completely down there. But practically, the probability of being beyond 4 is 0. And again, I could calculate that with the same type of procedures that I used for the other problems. It's just that 4 is off the chart, and since it's further out than 3.09, I'm going to approximate it by 1, because at 3.09 it's 0.999, and I want further out than 4. Now, if I said what's the probability z is less than 4, what's the probability of that? Well, that'd be the area to the left, or 1, or 100% probability.